Hi everyone. Today we're going to continue talking about geologic time, but move on from relative dating to absolute dating in this lecture. So we will continue to understand the difference between relative and numerical age, as well as calculate the half-life and use it to explain how we determine numerical ages, and then describe the basis for determining dates on a geologic time scale. So our geologic time scale, when we think of the history of the Earth, is broken into different periods. We have eons, which are hundreds or thousands of millions of years. So this is an eon. Inside of an eon, so within an eon, we have eras. So eras divide up the eon. Within eras, we have periods. And within periods, we have epochs. Rocks on Earth were found to be about 3.96 billion years old. We've actually found the mineral called zircons in ancient sandstones that were found in Australia, and those are dated to be between 4.1 and 4.2 billion years old. So this is the oldest rock and then mineral fragments that we have determined on the surface of the Earth, so far, anyway. We've actually then, using this same style of numerical dating, we're able to say that the Earth is about 4.57 billion years old, which correlates with meteorite findings as well as moon rocks that we've also been able to date using numerical or absolute dating. So how do we do that? How do we put a real number on a geologic timeline? In 1896, scientists discovered what we call radioactivity. And what this is it's the spontaneous emission of energy from atoms. So we can actually measure the changes in radioactivity within atoms in time. So this helps us determine the age of the atoms by determining how much they have changed. It will tell us how old they are. So a quick chemistry review before we get more into this. We need to understand isotopes. So all atoms of an element have an atomic number. And that atomic number is always the same for that element. So for example, carbon has an atomic number of 6. This means that carbon has 6 protons. This is not always the same for the atomic mass or the atomic weight, which in this case here for carbon-12 is about 12. This is carbon's, the number of protons, plus the number of neutrons. Meaning that here, if we know there are 6 protons and the weight is 12, that means there are also 6 neutrons, because 6 plus 6 would make that 12. Isotopes are elements that have varying number of neutrons. So the atomic number is going to be the same, but the atomic weight will be different. So the isotopes are defined by that atomic mass, and they're essentially different versions of the same element. So for example, carbon here has 3 different isotopes that can exist: carbon-12, carbon-13, and carbon-14. And the difference is carbon-13 has an extra neutron. Carbon-14 has 2 extra neutrons. So in this example of potassium-39, how many protons and how many neutrons are present? So potassium has an atomic number of 19, here we go, and it has 3 known isotopes, 39, 40, and 41. So here is an example of potassium-39. So how many protons and how many neutrons would we expect? This would have 19 protons. Actually, all of the isotopes are going to have 19 protons. And the neutron number is what is going to change. So for this example, 39, it's going to have 20 neutrons. So 20 plus 19 is going to make that 39. So radioactive decay. This is how we are able to use these isotopes in creating a numerical age. So isotopes can either be stable are unstable. Elements containing unstable nuclei are what we consider radioactive. And these unstable nuclei can randomly or spontaneously decay, which means they randomly break apart and produce a new element. So we call the original radioactive isotope the parent, and then the new element that it produces we call the daughter. So here you can see the decay makes this unstable isotope move from parent to daughter material. So there are lots of different types of decay, and we're not going to get into the details, but all of the decay releases energy. So the importance is one important thing is to remember that the original unstable isotope is called the parent, and what it creates through decay is called the daughter, or the daughter material. So what we really want to focus on is the rate of decay. So the decay is spontaneous. As I said, it's really impossible to determine for a specific individual atom, but scientists have been able to determine the overall or the average chance of decay for an atom over time. And what that is the half-life. So the half-life is the time it will take for half of the unstable nuclei to decay. So each isotope has a unique half-life. So each isotope takes a different amount of time to decay. And the half-life is what we consider the time it takes to decay by half. So the time it takes to go from fully parent material, for this case here, let's say it's 16 to 0. So it's 16 parent to 0 daughter. One half-life later, we have half parent, half daughter, so 8 to 8. Another half-life later, we take what was parent material and divide it in half. So now we have 4 parent left. Another half-life, we have 2 parent left. Another half-life, we have 1 parent left. And then we'd have half, and then we'd have a quarter. So each half-life, the number of parent goes down by half. So the number of that isotope goes down by half. So here is another example. If we are looking at percentage and we're looking at the parent isotope, here we start with 100% of our parent isotope. After 1 half-life, we're down to 50%. After 2 half-lives, we're down to 25%. After 3 half-lives, we're down to 12.5%. So each time you cut the parent material in half. And you're actually each time doubling the amount of daughter material. So here we see this, same graph again. So the percentage of radioactive atoms that decay during 1 half-life is always the same. It's always 50%. So it's always cut in half. And then here now we have 8, so it's cut in half again to 4. Another half-life, we have 4, we cut it in half to 2. So what we use to date different samples is to compare the ratio of the parent to daughter material. This is what's going to give us the age of the sample. Because we can tell from the ratio here how many half-lives have passed. If we know the age of the if we know the length of the half-life, we can then determine, okay, if 2 half-lives have passed, we just double the half-life. If half of a half-life has passed, we cut the half-life in half, and that is how old our sample is. So isotopic dating, the age can be determined by measuring that ratio of parent to daughter isotopes. And then we need to know the length of the half-life. So here are some examples of isotopes used in isotopic dating. And here are their corresponding half-lives. So this is already figured out. So when we go from potassium-40 to argon-40, the half-life, so for there to, is 1.3 billion years. So after 1.3 billion years, half of the potassium-40 would have decayed into argon-40. So let's do an easy example. We have a cup that is 100% ice. The ice has a half-life of 15 minutes. After 1 hour, how much of the original ice is left? The half-life is 15 minutes, and we're looking at 1 hour. That's 4 half-lives. So the half-life is 15 minutes. So after 15 minutes, after 1 half-life, we'd have 1/2 of a cup of ice, because we cut the 100% or the full cup in half. After a second half-life, we'd have 1/4 of a cup. So we cut that in half. After a third half-life, we cut that quarter in half, we get 1/8. After a fourth half-life, which would bring us to 60 minutes, we cut that 1/8 in half again, and we would have 1/16 of a cup left. One more example. We have the isotope Einsteinium-253, and it has a half-life of 20 days. You begin your experiment with 80 grams of this isotope. How much would you have left after 60 days? So the half-life is 20 days, and we're looking at a total of 60 days. That means 3 half-lives will have gone by. 3 half-lives, because 60, our total, divided by our half-life is 20, so we get 3. 3 half-lives have passed in order for us to get to 60 days. So this means after our first half-life, we will cut our 80-gram sample in half, so we will have 40 grams left. After a second half-life of 40 days, that 40 grams is cut in half to 20. After a third half-life, so now we're at 60 days, that 20 is cut in half and we have 10. So after 60 days, or after 3 half-lives, we would have 10 grams of Einsteinium-253 left remaining. So there are some other ways to calculate numerical age, which we won't get into too much in this class. Things such as annual growth rings from trees or shells. So tree rings or similarly growing annual rings that grow on shells, as well as layering that happens yearly or seasonally in sediment or in ice. So these are other things that can be counted to establish numerical dates. However, the range is super limited. For example, you can only use a tree ring to date back as far as that tree has been alive. So that's not something we can use way back in the past like we can with isotopic dating.